All right, we are going to switch gears a little bit. In section 5.6, we are back to dealing with limits, which is kind of a nice shift for a little while. And the limits specifically are in indeterminate forms. And there's a special rule that we'll have to do to deal with those. So those indeterminate forms that we're referencing are when we have a rational function that is either in the form 0 over 0 or infinity over infinity when we are approaching whatever specific limit we're looking at. So, for example, letter A here, if I plugged in -1 on the top and -1 in the bottom, it would give me 0 over 0. So when I plug it in, do the plug-in method, I get 0 over 0. So before we talk about L'Hopital's rule, which is the rule that we have to use to deal with these indeterminate forms, we always want to see if we can approach this from an algebraic standpoint, which is also how we dealt with it when we were just approaching limits to simplify. Because this one, sure, it's 0 over 0, which is definitely not a good thing, but if I just factor, do some algebra first, we are going to get to a much easier place to handle this. So I took a 2 out of the top, and then I recognize that I can factor the top to x plus 1, x minus 1 as the difference of squares. And the x plus 1's cancel, so I'm left with 2 times x minus 1, which I can certainly plug -1 into and get an answer. So when I plug -1 in, I get -4. So that's nothing new. This we should have been able to do in chapter 1 when we were talking about limits. Letter B we could not have done in chapter 1 because this is an infinite limit, but let's see if we know what to do here. So if I essentially plug in infinity, which is kind of a weird concept, but if we're looking at what the functions are doing at infinity, we're going to have infinity over infinity. So if we think back to the infinite limit rules, we're just talking about horizontal asymptotes. If we're doing a rational function at infinity, it's a horizontal asymptote. So since the powers are the same on the top and the bottom, we look at only the first terms here, the biggest power terms, and our limit is going to be 3/2 because of the coefficients. You divide the coefficients when the powers are the same. So now let's get into it when we can't do some sort of algebra or trick with the horizontal asymptotes. So we have f and g that are differentiable functions on the open interval from a to b, but they include c somewhere. Um, assuming that f prime is not equal to 0 for all of x in a of b except at c itself. If the limit of f over g as x approaches c produces the indeterminate form 0 over 0, then we are going to take the derivative of the top and the derivative of the bottom and find the limit again. If it's infinite again, just keep doing it. So this is L'Hopital's rule. Take the derivative of the top over the derivative of the bottom if we are in an indeterminate form. And that indeterminate forms also include one of these 4 listed on the bottom that deal with infinities. So let's get started and do a couple examples of that. So if I just plug 0 in, since we're finding the limit at 0, the first method always is just to plug in the 0. I get the top is 0 and the bottom is 0. So because it's an indeterminate form, we're going to take L'Hopital's rule, which I am going to indicate with LH so that we can tell that we took the derivative of the top and the bottom. The derivative of the top is 2e to the 2x, and the derivative of the bottom is 1. So now when I plug 2 in, 2e to the, or plug 0 in rather, I get 2 as my answer. Handy. That's nice. Okay, what about the indeterminate form infinity over infinity? So we really do have to understand the end behavior of a lot of basic functions. Like natural log x, we need to understand that that function is increasing as we approach infinity, and x is obviously increasing as we approach infinity. So in this one where we quote unquote plug infinity into the top and the bottom, The top goes to infinity and the bottom goes to infinity. So when that happens, we do L'Hopital's. Take the derivative of the top, which is 1 over x, and take the derivative of the bottom, which is 1. When I then think about what that function is doing at infinity, 1 over x is approaching 0 at infinity. And then obviously if we divide that by 1, we're still going to get 0. All right, getting the hang of it. So I did mention that sometimes we're going to have to do L'Hopital's more than once if it didn't work the first time. So first we're just going to think about, okay, I'm going to plug infinity in, or negative infinity in this case. The top is going to go to, at negative infinity, this goes to infinity, and e to the negative x goes to infinity as well as we go to negative infinity. So I'm going to do L'Hopital's. The top becomes 2x and the bottom becomes negative e to the negative x. Now as I plug in, quote unquote, plug in negative infinity, the top goes to negative infinity and the bottom goes to negative infinity. So that's still one of the indeterminate forms that we talked about. When we have an indeterminate form, we have to do L'Hopital's again. The top becomes 2 and the bottom becomes e to the negative x. Obviously 2 approaches 2 and e to the negative x, as we talked about before, approaches infinity. When we have a number over infinity, that is 0. Because we essentially think about that as a 2 on top and a very, 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 very large number on the bottom, which gives us an approximation of 0. Okay. What if we are not in that indeterminate form that they told us we have to do L'Hopital's? What if, like here, this is e to the negative x times the square root of x. If I plug in infinity, e to the negative x is going to be 0, and the square root of x is going to be infinity. So this is not the same form that they told us we should do L'Hopital's in. So we're going to do some function manipulation, just move some things around to get us into that one of those weird indeterminate forms. So without doing calculus, we're just rearranging this. I'm going to bring that negative exponent down to the bottom and make it positive. When I do that, the top becomes infinity at our limit and the bottom becomes infinity at our limit, which is one of our forms that we were told we could do L'Hopital's for. So let's go ahead and do L'Hopital's. The bottom, or the top becomes 1 over 2 square root of x, and the bottom stays e to the x. It might be better in situations like this to throw the double fraction together so we don't have a double fraction. So this is the same thing as 1 over 2 square root of x e to the x. Because when I look at it that way, and I have a constant on top and a very, very, very large number on the bottom, this is going to be approximated to 0. Okay, so that was fun. Let's do some that are actually hard. Some harder questions here. Okay, so this is going to be kind of a weird one. If I have a form 1 to the infinity, so if I plug in infinity, it's going to be, like the form says, 1 to infinity. So we are going to turn this into an equation. Y equals the limit as x approaches infinity of our original question. Because of that x to the x situation, remember what the trick is when we needed to get rid of that? We would do logarithmic differentiation. Who would think to do this? This is crazy. So when I take logarithmic differentiation, that means I'm going to take the natural log of both sides as they are. And then since I took the natural log of everything, that means I can do logarithmic properties. So I can get that x out of the exponent and bring it down to the front. Okay, so we're going to keep, just going to rearrange things a little bit, put our limit back out to the front. And then the x in front of the natural log since we brought that down to the front. There we go. Now that gives us the indeterminate form infinity times 0 if I was to plug in infinity here. So I need to make it one of the forms that L'Hopital's becomes possible for. So I'm going to, this is kind of a trick that we will have to use more than once. I'm going to bring that x down to the bottom. So leave all the natural log stuff. Whoops, purpose of taking that, there we go. That x down to the front, there we go. So the natural log stuff stays on top. And on bottom, I'm going to bring down 1 over x. Now, it seems kind of counterintuitive because it looks like we made the question harder. But if we bring that 1 over x down to the bottom and then plug in infinity, we're going to get 0 over 0, which is one of our indeterminate forms we can do L'Hopital's for. So let's go ahead and do L'Hopital's. Okay, so this is a natural log question. Remember, we have to do the derivative of the inside, which is negative 1 over x squared. Okay, let's try to make this little, this is kind of messy, especially with our amount of room we have right now. Okay, so what we did here was 1 over the inside, which is the 1 over the brackets, and then multiplied by the derivative of the inside, which is what we had on the outside of the brackets. And then on the bottom, we have the same negative 1 over x squared business, which is the derivative of the bottom. So since I have that negative 1 over x squared on both top and bottom, that can cancel out. And what I have remaining that I'm trying to find the limit of is 1 over 1 plus 1 over x. So did it make it harder? Kinda. That derivative was pretty nasty, but that's how we were able to find the limit, was because we turned it into an indeterminate form to do L'Hopital's. So I take the limit of this. Oops, I should probably say what we're taking the limit at. Notation, notation, notation. And this becomes 1. So now keep in mind that at the very beginning here we had natural log of y equals whatever this limit answer is. So natural log of y equals 1. Because at the very beginning we took the natural log of both sides to make this question possible, we have to remember that it's still there. And if I am to solve this for y, I'm going to get e, because I have to exponentiate both sides to get rid of the natural log. So even though my limit answer is 1, don't stop there. Don't forget that we did this natural log step way at the beginning. I have to keep that in mind and then solve for y. So y is e. Since way at the beginning we said that y is equal to our limit. Whew, that was a good one. Let's do that again. So here we have a form 0 to the 0 when I plug in 0 to the right. So I'm going to do that same trick. We're going to do logarithmic differentiation, and hopefully this time it isn't so weird. So we're going to say y equals the limit as x approaches 0 to the right of sine x to the x. And we're going to take the natural log of both sides. So this we can get that x out of the exponent. Okay, so our step here was we took the limit out of the brackets, put the natural log in, and brought that x down. That was kind of the rearranging step that we did at this point on the last question as well. So the x came down, and then we have the natural log of sine of x. All right, if I am in this form, it is not an indeterminate form in which I can do L'Hopital's. It's going to be 0 for the x and negative infinity for the natural log of sine. So what I need to do, again, is bring down that 1 over x. That's kind of a weird trick, but like I said, it's going to be kind of a common thing. If I can't get it into the, it's not in the form right away, I'm going to see if there's an x I can just bring down to the bottom as a 1 over x. I'll just up here state that we had 0 times negative infinity, which is why we had to change it. And this gives us negative infinity over infinity. Okay, so now that I have an indeterminate form, I'm going to do L'Hopital's. Natural log of sine. So that's going to simplify to cotangent because you do the derivative of the inside over the inside. And the bottom is negative 1 over x squared. This form is going to be 0 over 0. Oh, great. That means we have to do it again. I might actually, before we do L'Hopital's again, I might rearrange this. So this is just algebra step. This is not a derivative step. I'm going to get that negative 1 over x squared out of the bottom, make it a positive exponent, and then bring the cotangent down to the bottom and make it tangent. I just think those are going to be more comfortable derivatives for us to take. You can do that anytime as long as it's a legal algebraic step. If it makes it easier for you, go for it. Then we're going to do L'Hopital's again with what we have now. So that's negative 2x over secant squared. And finally, we're going to get that simplifying to 0. So we have to here remember that this is natural log of y equals 0, not our answer equals 0. So when I exponentiate, so y equals e to the 0 or 1. Fun. Okay, one more example. Infinity minus infinity. That is just straight up not at all what we want. We need indeterminate over indeterminate. So we can't have subtraction. If I see subtraction, I need to get a common denominator. So inside these parentheses, I'm going to get a common denominator, multiply that first fraction by x minus 1, and multiply the second fraction by natural log x. Okay, so what I really have now, once I get that common denominator, whoops, that's a 1, not a plus, is x minus 1 minus natural log x over our common denominator. So now when I look at what this would be if I was approaching 1 from the right, I'm going to get 0 on top and 0 on bottom. Yay, indeterminate form. So I can do L'Hopital's and make this a simpler equation to take the limit of. 1 minus 1 over x. And the bottom, unfortunately, is going to be a product rule. F g prime plus g f prime. So just to simplify a little bit, that is everything getting common denominator, so I don't have double fractions. When I plug in 1, I'm going to get 0 over 0. And let's do it one more time, see if it works with one more L'Hopital's. I'm going to get 1 on top and 1 plus, and again, we're going to have the product rule for the second half of the bottom. And if I plug in 1, at this point, I'm going to get 1 over 2. Yay! All right, and that was section 6 on L'Hopital's rule and indeterminate forms of limits.